Hey, hi. Hi, guys. So, yeah, good. I mean, reflecting on what all we covered, we think we have come to a good distance in 13 days. Reasonably good. I mean, we could have done it much faster, but it's like getting in depth with a few of the concepts and also covering majority of the concepts in supervised and supervised learning is nice, but few of the critical details are missing. Um, so I'll try to cover them today, tomorrow, most probably. Um, Most of it is will last ChatGPT and look at answers online and then learn them in a better way, because I've always been looking at it, but I think there is always some gap in the overall understanding on how people do it and stuff. So I would like to spend more time and understand it. Um, Before moving forward, I had one question when I was explaining k-means clustering yesterday. Um, I thought that is the answer, but I thought of cross validating it and saying it today. That is, let's say yesterday when we were looking on the plane, so in the plane we were actually putting all the points around. We picking up centroids and we are keeping that point. So in a single plane is okay. That means there is only for each point there is only one representation, right? Like some one value on the plane, right? So I mean, related to another point, there will be only one point. Our maximum, as it's a plane, we can consider 2 points, 2 features, x1, x2. But what if there are multiple features? What will happen? How do you pick up this thing? Is my question. So what happened is, I think the distance when there are multiple points, and how centroid is picked when there are multiple points, is if there are x1 to xn features, that means X is represented by X1 to Xn features. So one um, point or one row in the data set has n features, and we need to label them with a specific. So we should group them into one category and label them into one particular cluster, right? K means clustering. You should actually you end up creating, as we have seen yesterday, k clusters, and then we should put them into one cluster. So what we do it using centroids. Centroids are our means of segregating these into certain these many clusters. So centroid clusters are used for segregating or clustering this whole data set, right? So the centroids should, if we need to calculate distance from X, which has n features, to C, we can't pick C in as one point like C1, and then we can't calculate distance. That's not possible, right? There are n features. So what we do when we pick up a centroid, how many of our features are there which represent the X? We pick up the same number of features for centroid, that is C1, C2, C3, so all Cn, as one centroid. Each centroid will have n features based representation, and we calculate the distance between C and X of n features by following the Euclidean distance, um, which will be x1 minus c1 square plus x2 minus c2 square plus x3 minus c3 square, so on, x n minus en whole square root of this term is what is used as the distance, right? So that is used as calculation of distance, and from distance we, again, as you guys already know, we um, calculate the distance and then we pick up which one is nearest. We label it under that particular centroids cluster, and then for the all those points we calculate a mean. That means uh, if C will always be in that particular group of points, right, which are closest, and so it will be like, let's say x2, x5, or xa, xb. All those are points which in a group closest to a centroid C1. Then these some of these points by, let's say there are 200 points, 200 by divided 200 points. That's what mean is, right? So you calculate 200, and then C1 becomes C1 is equal to C1 plus all the x points by number of points plus one, number of x points plus one. So that's how we calculate the mean, and we derive the new C1, and that becomes a centroid, and from there we again repeat the whole calculation. That's how k-means clustering, excuse me, works, and that's what we have seen in that website as well. I should have bookmarked that website. That website is actually nice. That's okay, we'll see. And then that's with k-means clustering. So we are good with k-means clustering, so I kind of know how to, I think we can kind of know how to write a program for k-means clustering also. But I feel again k-means clustering doesn't sound much like a intelligence, right? It's more like a um, it's more like an algorithm, or it's more like an approach kind of stuff to find out which all points are nearest kind of stuff. So, is there intelligence on it? I doubt it. But do you recognize pattern out of it? Yes. So the whole machine learning, as I told you, is more about pattern recognition. So, and okay, now as we go to the next topic, when we say pattern recognition, what are we doing? We are recognizing the pattern in the training data, correct? But is what is our objective? Our objective is not to predict the training data, right? Because training data we already have responses. The objective is basing on this data that is there in hand, like the current x and y values that you have. Tomorrow, if you have an x which is unknown, say let's say it's unknown, it's not subset of this particular x, or it's not part of this particular x. When that unknown x comes in, how do you predict the y value, right? So you have all this x and y that you know here, and you got an x. That x is not, you see if it is there here, it's not there anywhere. Now how do you predict the y of this x is, you have pattern in the pattern recognition, you are representing the pattern using certain equation, right? So this unknown x, you put it into this particular pattern equation, and you derive y. That's the whole concept. That's how, that's nothing but that is what is called complex terms. They use models and predictions and all that will come, but it's simply a mathematical equation which represents the pattern of the given data. And when you take the input and put it into that particular pattern, it will give you the y value, and that is your prediction. So your objective of you should be very clear, or why you want to understand the pattern. Pattern is not about understanding how the data is distributed or something like that. The objective of machine learning and pattern recognition as part of machine learning is to predict a future unknown set of x that comes in, which is not overlapping with the current x features that you have, x feature data that you have, and we need to predict corresponding y. That's the whole objective. That is where you say how much is the pattern recognition close to what is supposed to be on y. uh, So moving forward in this topic, um, so we discussed on loss, right? So you thought this is the right pattern in which the x and y are related, right? And that's what you gave as one equation, right? I mean, as per your thinking, analysis, or predictions, or whatever, you thought this equation, this pattern is the right way to represent these points. um, but when you using that pattern, if you, for given x, all the x that are there, if you come up with some y um, as your prediction basing on the pattern recognition that you have, and if you see actual y that is provided by the team, because it's let's say it's a supervised learning, then the difference between them is what is you're losing, right? Because it's supposed to, you know already that it is supposed to be y1, and you predicted as yp1. So that means you are not right, correct? So there is difference in between yp and y1 and yp1, right? Y predicted one and y actual one. So that's actually considered as the loss, right? That's where you calculate the loss. And then to be effective, mathematically good and stuff, you calculate something called cost, like loss, cost, everything is towards the difference, finding the difference between y and yp. Now, let's talk of bias and variance. Okay, and let's ask ChatGPT and let's learn about bias and variance in detail. If ChatGPT doesn't answer to the detail, let's go to other website and learn it what is bias. And variance are two important concepts used to evaluate the performance of machine learning. Once bias measures how closely the average prediction of a model, the true value. Once a model with high bias tends to oversimplify the underlying pattern and run consistently on the predictor like the target variables. High bias can lead to underfitting, where model fails to capture the complexities of runs poorly on both our training and test datasets. Variance measures the variability or sensitivity prediction to changes in the training data. A model with high variance is so sensitive to small fluctuations in the training data and may show noise or random fluctuations instead of true patterns. High variance can lead to overfitting, where the model learns to memorize the training data rather than generalize as well. As that it performs well on. So that's the concept of bias and variance. So I think we discussed it, but in case if you have not discussed it, usually the data set, I mean, the simpler approach is we get a training data set. Um, like fundamental programming approach is always you write your code um, to address a specific problem statement and you try to solve it to the code. At the same time, you write some test cases which will actually test different scenarios within your code to make sure that it is working fine, and it also keeps the integrity of code when you make changes to it and stuff, right? So similarly, what we do when you get initial training data that you receive with x and y, we split it with certain ratio based on the data size and stuff. We take a call how do you want to split it. It's like actually an pure call of the whoever is the model, whoever is doing the modeling, he takes a call how much should be a training data, how much should be a test data. So and how to split the training data and test data so that the training data test data has good number of distribution of data kind of stuff. Those are all things which like are solving right now, but those are all the problems which has evolved initially. For example, let's say you say 80% of my data is training data and 20% is, that means let's say you have 10,000 records and 8,000 records you put it for training and 2,000 records you take it for testing purpose kind of stuff. So what might happen is, let's say if you take first 8,000 records and next 2,000 records as test data, the possible problem that you might see is the last 2,000 records, for some reason majority of them are on let's say the output is classification and the output is apples and oranges. Then let's say the test data is majorly on apples, like out of the 2,000, let's assume 1,600 or 1,500 to 1,600 are apples. Then what happens, you train on 8,000, that's okay, which is having a mix of data, but your test data, it is little biased towards apple. So if the model is, it actually evaluates more on the model's capability on predicting apple. So if you say anything orange, it will say most of the predictions on orange will go wrong because the test data is little biased towards apples. right? Because we create the algorithm based on training data, we calculate loss basing on training data and stuff, and we make sure we reduce the loss and cost kind of stuff, and finally we test it to say whether it is eligible to be published as a model which can actually predict generic incoming values and stuff. So we test it with the test data, and if the test data is biased to certain value, output value, what happens is the model in testing it fails because the expectation is maximum it tries to say it should be apples. So what we do, because it's failing for test data, we go back on training data and we tend to fine tune it, right? So as we fine tune it and then come and test with test data again, it will only go through test data when the predictions are much closer to apple. That is, even if there is orange, if it is saying apple for majority of the cases, then only it satisfies test data, and then the test data will go through, and you will be predicting properly and then publishing the model kind of stuff. Then what happens when you publish the model? Your model, because of this kind of a testing, it is little biased towards apples, and it would start predicting your orange and apples. Majority of the time it starts predicting it, saying they are apples. So your test data is also very important on how do the categorize. So what they would do is, if you use the libraries like scikit-learn or anything like that, they are just machine learning libraries. Whatever we are discussing now, they converted them into code and they put it there so that we need not write code for all of these kind of actions that we do repeatedly. Initially people used to code everything line to line kind of stuff. Initially when I started machine learning long back, we were writing actually code in Octave to solve these problems. People used to write programming in R, Octave, Python, Java, multiple languages in which they were writing code for this. But what happened is there is some repeated code, like splitting a test data and training data, calculating loss, calculating cost, deriving certain equations. There are a lot of things that we do as part of our during data analysis. We do certain things. All of them, what they have done is they've coded it and given it as a generic method within the and build them all as a library, so that you need not reinvent the wheel, right? There is already a code that is written. The code again is optimized based on different techniques that are published. um, mm, so all that is adopted and stuff. You need not redo all those things, so they are there as part of libraries. And like few libraries like TensorFlow and stuff. So all these libraries that you listen to, TensorFlow, scikit-learn, Keras, everything is nothing but all these topics that we're discussing. They have coded it and they've written it, and this code, as it deals with huge amount of data, and it requires a lot of compute and stuff. They optimize the libraries code in a way they can actually process huge amount of data, and they can actually run efficiently, use the compute resources. Okay, so that's the difference between different libraries. Why did we create multiple libraries? That is the difference. Um, mm, like the getting into compute resources like CPU, GPUs, and all that stuff are there, right? So efficiently using their capabilities and to run and deliver results will be the primary concern into which the different libraries are made. Okay, coming back on bias and variance, and training data and test data. So what happens is you create a pattern, and the pattern, our objective is to reduce the loss. So you can reduce the loss, but the question comes down to how much you can reduce it. So as we have seen yesterday, um, when we are doing k-means clustering, um, after a certain point the centroid is not moving because the average and the centroid are very close. At certain point you can see how much it is moving, and even the visually we can't see that it is not moving. It's not that it is not moving, it still might be moving, but maybe a little bit, very small, that we can't even see on the screen. Like Visually we might not able to see, but it might be still moving. The point is, the more you get to it, the more you get to a position where it is overall loss is that small that it is very close to minimal. The You are actually your equation that predicts the pattern is getting much closer to the division, like let's say classification. The loss, if it is getting closer to zero, that means you are ideally categorizing the two apples and oranges kind of stuff, right? But what happens is, that is what is called overfitting, where for the training data. So to put it simply, focus on the training data. um, if your model or pattern that is created, that equation classifies um, the training data, the more it tries to answer let's say the loss is less, means that means the y and yp are very close by. And majority of them, if it is able to predict properly, then what we are going towards is the uh, model is actually more um, tuned for the training data. So then what happens, if there is an unknown data that comes in, especially if that unknown data is outside the boundary of training data, the predictions are actually the predictions are not might not be correct, because the equation that you built is specifically done for this training data. As soon as you take it and put it into test data, what happens is, test data being outside the boundaries, and preferably, let's say that the training test data has certain values outside the boundaries of the training data, the predictions will not be good, right? Because we what we do, if there are blue dots and then red dots, we draw a line, which is okay. I can actually show you the image here. So if you see, yeah, this is the standard example. um, so if you see these points that are there, I said, what's the pattern recognition of the given points is what we will try to. If you look at it, all three of them are trying to do pattern recognition. The loss is basing on y to yp, right? So let's say these x are representing the y, that is price, right? So this line is our pattern, which gives us yp. If you look at all three diagrams, you can clearly see that here, first one, the loss is high. Second one, there is some loss, it's not like perfect. Third one is perfect, right? So typically in programming, what we do, our objective is always perfection, right? If there are 100 test cases, we try to 100 scenarios, we try to program in a way that all the 100 scenarios are covered. But here in machine learning, in the pattern recognition, we are not dealing there. You know the scenarios, you know the test, you incoming data, and you code for it. Here the challenge is, where the intelligence comes into picture, is intelligence is where you infer the values for the future values that are coming in, which might not be same or equivalent to what you have in hand right now. So you don't know all the possible scenarios, so you can't expect to uh, fit in the current training data perfectly, like on the third one, and say that it is correct, because the future values you may not exactly have this pattern, right? You might have 100,000 records. Like, let's say you are trying to predict the um, uh, potential probability of a person becoming a millionaire. Okay. So you take certain features, like what's his current credit score, so what is his overall financial performance, what is his earning capabilities, how it is your spending capability. There are a lot of metrics that you take and then you spend it. But you're doing it for 100,000 people. How many people are there out there? Means there are millions of people. Like, then if you fit in your data to this 100,000 people, out of the remaining million of people, there could be anywhere, and your this line that you're drawing here, this might not exactly fit in for them, right? So those guys are there, those guys are there, could be anywhere. So this is called overfitting, where y and yp are almost close. See, this point is a little bit outside, but the remaining, we are putting it like this. We can tweak our equation in a way that the equation could actually cover all the points. Okay, but this is overfitting, so we don't want this to happen. At the same time, this is underfitting. That is, for training data itself, if it is not, if the predictions are that far from the actuals, obviously on test data it will be bad. Most probably it will be bad. Third, even future data that is coming in, we are not even recognizing that. We are not even getting close to a pattern of this particular points, right? We are randomly giving some equation saying, okay, this itself is close to the points. So that also doesn't work. The second, so here it is high bias. So when and high bias is underfitting, high variance is overfitting. So bias is where the values predicted are far from actual wise. Variance is somewhere where the predicted values on training data is very close to the actual values. So bias and variance are the terms, not very important, but to communicate with people. Like, I built a model. It has I think it has high variance, so I'm not sure how far it will predict the values for future. Same time, same point can be said for high bias also, saying I have created a model, it has high bias, I'm not sure how far it predicts the values for the future values that are coming. So high bias and high variance both are problems. So where should you go is low bias and low variance. The question will be how to create low bias and low variance, right? We'll get to that. Like, what's good fitting kind of stuff, right? So good fitting comes in where there is loss, but the loss is reasonably minimal. That it actually does predict values, but they are close to the y, not too far. And when you say pattern, a pattern is different from finding drawing an equation for a given line points, right? So why didn't we see again all this math where we learned given points? uh, if you draw a line connecting all those points, that actually gives you the pattern. Uh, that actually gives you an equation for all those points. That is possible. Given 100,000 points also, you can draw a line which actually goes through all those points. It is technically possible to arrive at an equation like that, like the way you see here, right? But we are not saying draw a line or recognize a equation which actually which goes through all these points, is what this not the term that we're using for machine learning. That is what we use in math, right? In math, they give you 5 points, and if there is a line that goes through these 5 points, what is the equation of the line? That's what they'll say. So we derive that equation, blah 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 blah. But here in machine learning, from day one, we are not telling that, okay, draw a line which goes through all the points. We are saying find the pattern of the points. So if you see, you why this is a best model which is good fitting is, it sees that the points are starting as the size is small, the price is small, and it is growing in this pathway. Okay, so that's the reason the input data set is also very important, for getting a So for example, in this points, let's say if you remove if you remove this point, right? So what might happen is the line could come like this. It's also possible, right? The line could come like this, like it could start from here and it could go like this, and then it could go maybe from here straight like this. That will also be very close to these 4 points if you remove this point. So the because this point is coming here, and if you draw a line like this which is covering these 4 points, it will be further from this. So what happens, this point and your line prediction, if it goes like this, these two are far away. That means you have loss is calculated based on the overall points that are there. So what you do, you push that line closer to this so that the loss is minimal, right? But at the same time, we don't want this. Okay. So what happens? You keep a line which is actually closer, as much as possible, closer to all the points, but not covering all the points, so that that gives actually a pattern that's saying, given this 100,000 points, I think they are all distributed in space in this format, in this curve, right? Or using different planes, we say maybe these are all falling under these planes. Or if you if you go with the decision tree or something like that, which says actually these points are segregated, are classified based on these lines, this set of lines, not just, I mean, need not necessarily, we should recognize the learning with decision trees is that in linear regression, logistic regression, we are actually trying to fit in, we were trying to draw one line for all the features which are actually in multi-dimension. If they are in one dimension, drawing the line is easy, but if they are in multi-dimension, drawing a line is impossible. Then comes a plane, which is also possible, but even with one plane, you can't you can't create a plane which goes through multi dimensions, right? Like too many, you can't. So that is where to address, as the number of training data sets that are coming in with multiple features are increasing, they understood saying there might be a need that we need to address these, solve this will be a combination of multiple equations. As well as in decision tree, what happens, first you take one feature and then draw one line, x1 is equal to a, and then you use another line to classify it further. X2 is equal to b, x3 is equal to c, like that you've seen the decision tree. Right, so that's how we can use multiple equations together also to solve the problem. So because it's never restricted that you should go with one single equation, you can have multiple equations. The objective is to recognize the pattern. So there, if you look at it, the lines are like this. If you put all of those lines together, it's like you can shoot you should see all of them together forming like one line or one pattern kind of stuff. So finding the pattern is the major thing, but not finding the line that goes through all those points. So this is very very important point. If you are there on the right side or on the left side, your model's prediction capabilities to future unknown are lower. That's that's the way you should deal with unknown data, right? So here what they're doing, they know that there is loss, they know how to fit in further, but still they are saying, okay, this is good enough, this equation is good enough, that it is closest to the points that has been given. At the same time, it's generalized the ones like you, AGI is the famous word in generative AI now that people are open AI and everybody's focused on going there. The full form of it is artificial general intelligence. That is, this AI or machine learning, as I said, it's more towards this data. For a known data, you fetch intelligence which is specific to that particular data like this, and you predict unknown values basing on that. That means that is how it is. But whereas generalization of this particular model is where it not only solves the problem for this particular data, it solves the problem for different data as well. And it also is generalized in a way that if there are new points coming in, it can actually accommodate. The loss is not only minimal for this, but if you calculate loss for the new point that is coming in, for that also the loss is minimal. So that's where you go for generalization. The more generalized it is, the more it could actually solve more number of problems. Imagine I create an equation which draws a line which not only solves this data set, but it could solve data sets. It's generalized that it can solve multiple data sets. Then it is, the more it is accommodating multiple, it is more generalized, right? Like model that's solving this particular problem, it's solving multiple problems kind of stuff. Means, I mean, it doesn't work like that, but I'm just saying, there is a there's a model that predicts between apples and oranges, and as we generalize, its capabilities are, it can actually classify any fruits. That's one level of generalization. It can classify any fruits and vegetables. Second level of generalization, it can classify any fruits, vegetables, and maybe cooked food. So your model, as it tries to adopt more and more capabilities of classifying or predicting values, it is more being generalized. That means um, it can cover actually higher ground with respect to either classification or regression predictions or anything like that. It can cover higher ground the more it covers. So now with ChatGPT and Gen AI and all that we are talking about, is it's not specific to a use case. Previously, it's like if you are trying to predict something in medical domain, there used to be models which are specifically built for medical domain. If you are trying to do something with education, it's trying to do something with respect to safety, security, vulnerability detections, mm, fraud, phishing detections, all this. For everything, there used to be models which are specific to the particular domain, and the models used to be fine tuned to be very um, um, have high accuracy for that specific domain and stuff. So now those are not sufficient because we ended up saying, if you go online in the model repositories and stuff, there are almost lakhs of or millions of models which predict something, and they're very specific to certain topic. But the challenge is, in a given topic also there are lot of models. So how do we maintain these models? Again, let's say today we build those models, and then tomorrow if you get more data, this 1 million models either should be automated to retrain themselves on the new data that is coming in, or there should be some people who are addressing all this, and they should manually update all these models to learn these things to predict something, right? So um, it's a tougher if it's a tougher exercise to maintain all these models to do certain predictions. And with evolving data, like let's say you train with the data that is available till 2000, and and now if you use the same model and try to predict things, is far different from 2000. So your model's predictions will obviously go off, right? So you should actually retrain. That's called retraining your model time to time, so that your model is up to date with the latest information, and it will learn more from the mistakes it has done, and also learns more from the new like. So these are the points. And now what happens, there are points like, there are a few points that come in this level also. Then what happens, that means the prices are, the size is, even though it is big, there are prices which are going lower as well. Then what happens to this curve is, this curve actually bends down and goes in between these two, or it might go like this. And assuming this is the only odd and the rest of them are coming close, then it would bend down, because people are not interested in buying big size houses maybe, and the prices will go down there, because the property tax in that particular state, they would have increased it. There could be a number of factors why, but the it could change based on adding the new data. The equation will definitely change, and that will help us. So adding more test data is always good, but generalizing, retraining is continuous exercise. But again, retraining is a big exercise, and it's a lifelong process. It's not just one time when we sit and then say, okay, you do key points, you cluster it and stuff. It's not good enough. It's going to be a lifelong exercise where data keeps coming and you need to keep rebuilding. People got fed up saying how many models are there and how many models will we train, and how many people will take ownership of training them all the time, because uh, let's say there is some model that people are all relying on. They would have put it somewhere and then they published API and stuff, and then he is not retraining it. You are actually predicting basing on stale data. That's not, it's not accurate, right? So people were being pushed on building these generalized models which has multiple capabilities within it. So uh, that's where the so-called AGI concept is coming in, where it has generalized intelligence in a way which can actually talk of multiple domains, able to answer questions in multiple domains. It adopts to those multiple things where we need not even worry about asking different models for different solutions, kind of stuff, right? That's AGI. But coming back on this high bias, high variance, and underfitting, overfitting kind of stuff. So the next logical thing to understand is what would we do to address this, right? So usual thing is, you if there is high variance, then what they would do is they will actually try to add more data to it. Once you add more data to it, what happens is the equation by itself will um, adopt in a way that um, it tries to fit into the remaining points, and it will move away from these points, right? So that's the logic, right? So then it would more come towards the low variance side. Second, on high bias, what happens is, so you deal with variance using data. There could be other techniques as well, but whatever I remember on top of it, I'm giving you. Coming to high bias, if it's very generic, like straight line that you're drawing to gather points which are very highly distributed, like that, not like this, but more distributed like this, then we will actually try to modify the algorithm instead of going for single degree, first degree polynomial. You go to multiple degree polynomial. You will try to add more new features. Like that, what you do, you focus on improving your equation, or pattern recognition equation, in a way that it actually is gets closer to the points by using loss and stuff. So that should move towards low bias. So left to center and right center is the. Yep. So this explains variance, bias, high, overfitting, underfitting kind of stuff. So let's ask ChatGPT also once, and what are the different techniques used to address overfitting and underfitting, or bias and variance. Addressing overfitting and underfitting, or balancing bias and variance involves various techniques in improving generalization. We talked of generalization, right? Performance of machine learning models. Here are some common techniques. Regularization. Next, regularization. We thought of talking about regularization, right? So regularization techniques adds a penalty term to the model's loss function to discourage overly complex models. So what happens, we are doing y minus yp, so we are trying to take y minus yp to closer to zero. We don't want it to be zero, correct? Y minus yp should not be zero. That y minus yp is zero is overfitting. Y minus yp too high is underfitting. So we know how to go to zero, we don't know how to stop. If we want to stop before, underfitting and good fitting is there, but we don't know when we are in underfitting, when we are in good fitting, right? So what we do, we take a small term we add certain term to the loss where whatever you do, the loss is always there. It can't make it zero, right? So what they do to the loss function itself, they'll add certain additional penalty term, right? So the penalty term will say that, boss, irrespective of whatever you do, the penalty, there's always some value to it. So people don't have a choice. How much ever they tune it, they can go to y minus yp. I mean, they can over tune it to a way that it becomes y minus yp is equal to some negative value to take out the penalty as well. But um, that there's a different story. I'll say how the penalty also is varying basing on the equation kind of stuff. So the penalty is not always static. The penalty that we add here is also varying. How it varies and stuff, we'll look at few of the regularization, and most probably we'll cover them tomorrow because we are a lot of time. Different types of regulations and stuff, those are also interesting thing, and we should learn why there are different types of regulations. Why not penalties plus c, loss function plus certain constant value c? Why not? Why, how will have different will regularization? We'll see it. So we have something called L1 regulation, L2 regulation, lasso, ridge, use techniques. These techniques help prevent overfitting by reducing the magnitude of the model parameters. Okay. Now, cross validation. So, cross validation technique is such as a k-fold cross validation split. So, what we do in cross validation is we split the particular data set into uh, smaller chunks of smaller data sets. And when we train the data, we don't train on the overall data. So that is, the pattern recognition doesn't work on the overall data. You break it down, and we train the model for each of these points at one go. Like, you break it down into 5 sets, and you train the model for 5 sets, different subsets of the data, and we evaluate performance on 5 of them. Okay. That's a more reliable estimate of the model's performance. It helps detect overfitting by assessing how well the model generalizes to unseen data. So that means, um, instead of having trained set data and test data, you are actually training itself, you're doing in multiple data sets. So for one first data, when it comes, it says, okay, this is, it might be the line. And if you, that's an equation, right? So it doesn't fit, it doesn't lie only for that points. In the previous exercise where you've seen the point pattern, you have seen the line like this, but what you should see is it will go like, go below, like same equation, it will go down and it will also go up. For you to look at it, they have drawn the line only for the piece where you have equation, but what happens, it can go down, go up. So but what we are doing, we're breaking down those points into few points. We draw a pattern for each of those points, but those, that line, they are generalizing it. They try to retrain it so that instead of going like this, it might take a curve because of the new data set, that new sub data set, that is cross validation is breaking down to k fold, right? Each fold comes in, and then it bends that line in a way that it is closer to that particular subset kind of stuff. So, and everybody, all the k points try to tweak the model in a way that it is towards, it is closer to all those points, uh, but separate, it is not closer to the overall data set. That when you have 100,000 records, if you want to draw a line which is closer to all 100,000, the iterations will also be very high. And in the when the iterations are high, you you reduce the loss. The more you reduce the loss, you're going to overfitting. So what they have done, they've broken down all those points, and now the iterations are low, but you train with all those subset of models, and you try to get closure individually to each subset. So you don't get into this overfitting problem for all the points. You overfit to subset of the points, but not the overall points kind of stuff. Okay. So that's cross validation. I think that was more generic explanation, but when we do it, we can understand. But cross validation is one approach to address overfitting anomaly. Early stopping. Early stopping involves the early stopping. Again, early stopping is like if you draw a graph and if you see how the each iteration is improving or reducing the loss, like the cost function. You remember when we do gradient descent, we start from one point and then you go down, right? We keep going down until you reach a point where from there, if you go any direction, the loss is increasing but not decreasing. So you keep going down in a path where where the loss is decreasing. But if you reach a certain point that you move on any direction, the loss is higher, then you are good. But what we could do is to, if loss is minimal or closer to zero, that means you are overfitting, correct? And so what you need to do is you need to go two or three steps behind backwards, right? Then you know that is where you are more generalized, you are not overfitting. So that's like early stopping. You don't go till your local optimal. You stop like three or four before reaching the local optimal. So model performance on a validation set during training and stopping the training process when the performance starts to degrade. It helps prevent overfitting by avoiding training the model for too many epochs, thus preventing it from memorizing the training data. Got it? So epochs is nothing but the iterations, the number of iterations in which we train that particular the number of steps. Like in gradient descent, if you see, we do number of steps. In k-means clustering also we do number of um, loops, right? In which we keep moving the centroid. These are all are in we'll future talk about neural networks and stuff. But the iterations in which we do to retrain the training data set in a way that it the pattern recognition is much closer to the actual pattern, right? Feature selection technique aim to identify and select the most relevant features for the model, which discarding the irrelevant or redundant features. By reducing the dimensionality of the input space, the feature selection helps at the risk of overfitting and improves model generalization. Okay. Ensemble models. Ensemble models combine multiple base models to form a stronger, more robust model. Techniques like bagging, random forest, boosting, like boost, gradient boosting, and stacking combine. This bagging, boosting, and stacking techniques are very important. So I think we should learn them clearly, each of them, what is bagging technique, what is boosting technique, and what is stack. And we should also um, see a practical example on how bagging improves the performance, how boosting improves the performance, how stacking improves the performance. Second important thing that we need to learn there is when to use what. When should I use bagging technique? When should I use boosting technique? And when should I use stacking technique? When you go for ensemble models. Ensemble models, if you recollect, it's usage of multiple models of using one model and then like you you have some predictions to do, like you, like we have a health problem, we go to one doctor, right? Instead of relying on the doctor's response, you cross validate it with not cross validation, but you go to multiple doctors just to make sure that the prediction is same. If there is differences, then you should address why there is differences, and you again reach out to these people or something like that, right? So uh, it's like that, like talking to multiple experts on a specific thing to before predicting. So each model, let's assume that it is an expert. So each model's classification, let's say this model says apple, this model says apple, this model says orange, then you go with majority, right? Or you have some incremental value, you get predict the incremental value, take an average of it or something like that on how much you. So the model selection is also very important. Then pruning is a technique used in decision trees to remove unnecessary branches or nodes from the tree, um, to help preventing overfitting. So decision trees, what happens? It's if you do it, if you create a tree which has all the features in it, then what happens? It is perfectly fitting. There's no way everything should be classified. For the training set, it will be 100% match. But what we want is we don't want 100% match to happen. So if you don't want the 100% match to happen, what you need to do, you need to remove certain branches. That is the only way. But how, which branches to remove? How do you remove? It's more like, that's what you call as pruning, saying you remove some nodes, you remove some branches, and something like that. We should also know how do you remove them. So usually it is most probably random. You randomly remove few points. But what happens, you might be removing some nodes or some branches which are very important in the prediction. Sometimes maybe you remove a branch and then that actually has the whole class C or class D is classification there. Now what happens, your overall model stops predicting class C and class D. Okay, that's it for today, guys. We will we will continue the remaining tomorrow. Yeah, bye.